all possible routes. Let me first play the problem. Yeah, because for this problem we need to use a modular. Yeah, let me just prepare a modular first in case if I forget about it. So it's gonna be 10 to the power of 9, 10 to the power of 9 plus 7. Now let's try to understand the problem. So we are given a locations array, and we are starting at the start point. It is 1, so it is just like from index 1, and we're gonna go to the finish. The finish is 3, it is 8. So 3 to 8. Let me make a drawing. So yeah, first of all, we are starting at this index 1, it is 3, and then we're gonna go to the finish. It is index 3, and it is 8. And so the distance is the fill. The fill is 5, so the distance 8 minus 3, it is 5. But we're gonna check the absolute value because it is coming from here. But we cannot start at the same point. I mean, for the next step, we have to move left or right, but we cannot stay at the same position. So this is not allowed. Otherwise, there will be a dead loop. It can never go out of the loop. Yeah, for the DFS, because later on I'm gonna write a DP. Basically, it is a DFS plus memorization. But we have a limit. We cannot exceed the fill. It means our fill, the use of the fill, it should always be less than or equal to the fill, this 5. Yeah, and we can check there are many rules. For example, 1 to 3, 1 to 2 to 3. So this means 3 to 6 to 8. Yeah, 6 minus 3, 8 minus 6. So the sum of them is still 5. 1 4 3, it is also possible. So 2 to 4 and to 8. 1 to 3. Yeah, let me check 1 to 4. So yeah, it is 3 to 4 to 8. So sum of them is still 5. And 1 to 4 to 2. So this is 3 to this 4. It is 1 to 2. 6. 1 plus 2. It is 3. And then we're gonna go to 3. It is 5. So sum of all those values should be 5. So this is the total possible cases. So it's gonna be 4. Now we are going to find all the possible cases. How can we find that? Yeah, basically we're gonna find a brute force idea. So the brute force idea is we're gonna starting from the yeah, let me make it clear it and make the drawing again. Yeah, let me clear it first and draw it again. So we're gonna start at the starting point. The starting point is 1. So we're gonna start at here. Now we are going to check. We're gonna check all the possible cases, but except this one, because we are standing at this position here. We cannot stand at the same place. We have to move left or right. Yeah, maybe for the next step, maybe it is 6. Yeah, and then I'm gonna check from this 6 to left or right. I'm gonna check all the different cases, but I cannot check 6 again. Maybe next step is 8. So I'm gonna check the sum of all the values. So from 3 to 6, it is 3 absolute value. 6 to 8, absolute value is 2. So 3 plus 2 is 5. So this 5 is less than and equal to the fill. But we've also already returned. But we've already go to the finished position. It is the index 3. So we're gonna return a result. Yeah. So if we go to the finished position, normally we're gonna return a result. We're gonna check this fill. If our fill used is less than or equal to the provided fill, so we're gonna return a result. So this is one possible result. We're gonna return 1. If it is more than the fill, for example, the fill is 5, we get 6. 6 more than 5, so we're gonna return a 0. Yeah. So this is basically for the DFS part. But there's also other edge cases I'm gonna explain later. So for example, in the example 3, so yeah, we're gonna in example 2, for example, we can go 1 to 0, 1 to 0, 1 to 0. We still use the fill 5, but this is a still valid path. Yeah, we're gonna I will solve this one in my code later. But let's go to the main function of the code. So I'm gonna define a DFS. So for this DFS, I'm gonna write a path first. Yeah. Now finally I'm gonna return this DFS. So inside of the DFS, I'm gonna prepare a starting point. It's gonna be the start index, and I'm gonna prepare a f. This f is the field used. So from the beginning, my starting point is just this is also start, right? I'm gonna use an index I as a start, and the field I'm gonna start in from 0. Yeah, so here is f, here is I, and this is the start, and the starting point is 0. So I'm going to call the DFS with start and with the field used, which is from the beginning, it is 0. Yeah, normally this is a DP problem, so I'm going to use a cas. Yeah, now let's go to the main function. So the main function would be, we need to check some edge cases first. So for example, yeah, we're going to return something if we find a finished position. If we can go to the finished position, for example, index 3. If we can go to the index 3, we're going to return something. But how can we return? We have to check. So if this f equals to finish, basically this means we've already returned to this position. Then we're going to check if this path is valid or not. So we're going to check this f. Yeah, we're going to, it's not f, it is I, because I is my position. If I equals to finish, it means from the starting point I've already reached the finish. And then I'm going to check this f. If this f is less than or equal to the field, I'm going to return a 1. Otherwise, I'm going to return a 0. Yeah, currently I'm going to write it like that, but later on I will change it if something is wrong. For example, if the example 2 cannot pass, because basically this is 1 0 1 0. If I reach the finished position, I cannot return it immediately. I have to do something before I return it. Yeah, but currently I will write it like that. I just want to check if it can pass for the first example or not, or if it can pass for the third example or not. Yeah, because in those examples there's no forward and backward at 2 points. Yeah. Now I'm gonna check if the field is more than the field. So what about if the field is more than field? I'm gonna return a 0. This just means there's no path. So I'm gonna plus a 0. Now I'm gonna prepare a result, and I will accumulate all the possible paths. So for j in reach I cannot start at the same point, so I have to check if j are not equal to I. So if this is j not equal to I, basically this means I will go forward to the DFS. So what is going to be the DFS? It's going to be result plus all the possible paths. So for example, I'm starting from index 1. I'm going to check all the possible cases. Yeah, so the result would plus equal to the DFS. So inside, I will go to the position j, and what is my field? Yeah, so my field is just like from the beginning, field plus the absolute value of locations I minus j or j minus I. It is the same, yeah, because we use the absolute value. And finally, we just need to return this result. Yeah, our final result should be modular a mod. So this is the basic function for this problem. Yeah, let me just have a roughly check and before submitting the problem. Although here is not right, but I will change it later. I just wanted to check if I can pass the example 1 or not. Yeah, it seems I didn't pass the example 1. It means there's something wrong with it. My output is 0. Yeah, let me check it. So for j in reach I, if j not equal to I, result should plus DFS with this j. and f plus absolute value locations I minus location j, and finally I will return this result. My final return would be from the starting point. Yeah, let me just talk about this I. I'm gonna print this I and print the f. Yeah, basically there should be nothing. I didn't print out anything. This means I didn't find a finish. Yeah, I didn't even find a finish position. So even my j updated, but I didn't find a finish position. Yeah, let me just check if there's anything inside my function. What is wrong with it? Yeah, there's something. So from the beginning it is 1 0. Yeah, so here is 1 0. So from here it is okay. So the result it is I equal to 1. So for j, yeah, this is y. Yeah, because I have to check all the points, not just from I. This is why. So sometimes if you find something wrong with it, you have to print out and check what is wrong with it. Yeah. Yeah. Let me just recover the print. I need to basically delete all this print because I know I've made a mistake from here. So from here, I need to change it to n. Yeah, because I need to check all the points. It's not just from I. Yeah, because there is actually there's a sequence for the locations. Basically, we cannot change the. Yeah, I'm not sure if I can change the sequence, but even if I change the sequence, it should have no influence to my solution because basically this is a DP problem. Yeah, so I don't need to change the sequence operations. I'm not sure. Maybe it's gonna be a little bit faster. Yeah, because basically I use the DFS. Yeah, but I will change the sequences later. I cannot not change the sequence because my start position is fixed and my finish position is also fixed. Yeah, so I cannot change the positions. The sequence must be the same as the locations. Yeah, so I need to prepare a variable n. It will be the length of the locations. Now I have to check again. Yeah, now as you can see, luckily I passed the first case. Yeah, because there is still a lot of testing cases for the example 1. I passed the example 1, but I didn't pass the example 2. And this is also straightforward. Because for my function, I didn't check if I go to the finish, it means I'm gonna return a result. But basically from here, you can see 0, 1, 1, 0, 1, 0. Yeah, it means I go to the finish position, but I go out and go to the finish position again. But for my function, I cannot do that. I can only use one time. So for example, 1 to 0 or 1 to 2 to 0 or 1 to 2 to 1. But if I go to a 0, I find a 0, I have to return my final result. So this is why I return 3, not 5. As you can see here, I return my output is 3, but the expected result is 5. So this means that those two result is wrong. So that is coming from here. Coming from here, I cannot return 1 immediately. I have to return all the possible cases. Even this f is less than the foo, I can still run the DFS. Yeah. So from here, basically I'm gonna check the DFS again. So let me copy the code. So basically it is like that. Yeah. I have to copy the code. Yeah, because I didn't find. Because I write it for myself. I didn't check any answers. Maybe there's a better solution, but at least for me, I will use this way to solve this kind of this kind of testing cases. Yeah, it means if I find 0, I can still go out and go to 0 again. So from here, if this field is less than or equal to the field, if this f, so I'm going to prepare an answer, and my answer will accumulate all the possible values, and finally I'm going to return 1 plus answer. Yeah, before I return 1, because it is not finished yet, I have to check all other cases. So from the answer equal to 0, and I'm still gonna prepare a for loop for z in raise n if z not equal to I. So the answer will accumulate all the possible results. Yeah, so this is the entire code. Let me just run it to check. Now as you can see, it works. Yeah, basically I just need to copy here to here. Now let me submit it to check if it can pass all the testing cases. As you can see, it passed all the testing cases, and the speed is okay. For me, 1 second is okay. So the time complexity, we need to be careful about this one. So the time complexity, let's say this is n, and this f, let's check the f is 200. Let's say it is also n. So this is n squared, I times f, n squared, and here is a for loop. So it is n cubic. Yeah, so from here it is n cubic. Yeah, but for here, we want to return, for this DFS, we want to return a final result, but our DFS still go inside the loop to check if there's still other things to check. But it is not n to the power of 4, I think it is still n to the power of 3, because this field will be decreased for each of the time. Yeah, and even for here, yeah, basically because I'm writing this kind of a function, it's a little bit difficult to analyze the time complexity. Yeah, but even from here, so this is n cubic. If n cubic comes here, if I equal to the finish, I have to check something from here. Yeah, if it is less than the finish, I have to go out and go inside again. Yeah, so technically I think this is a on to the power of 4, but it should be less than that. Yeah, so that's for it. Yeah, so the problem is not so difficult, but for me, if I write a function like that, it's difficult to analyze the time complexity. I have to analyze it carefully. So from here it is n cubic, but if I go inside, I have to check something from here. Although it is not every time I have to check, but there's some testing cases like this. I have to go inside and go outside. Yeah, so I have to say it is n to the power of 4. Thank you for watching. See you next time.